An educator believes that the new writing activities in the classroom will help elementary school pupils improve their reading ability. She arranges a third grade class of 21 students and follows these activities for an 8-week period. The control classroom of 23 third graders has followed the same curriculum without these activities. At the end of an 8 weeks, all students are given a degree of reading power test, which measures the aspects of reading ability that the treatment was designed to improve. Here are the data. Is there good evidence that the reading activities produced increased reading levels? So our goal is to prove that these numbers are higher than these numbers. Well, this is what we do. First, we have a null hypothesis. Our null hypothesis would be that the mean of the treatment is greater than the mean of the control. No, that's not right. That's what we want to prove. Our null hypothesis would be that they're equal. Great. What we want to prove is the mean of our treatment is greater than the mean of C. Then we have to write this out. The mean score of the classroom that use the new learning techniques. Now the other one is the same thing, but they did not use those new learning techniques. That did not use. All right, so now we defined our means. Now we go and look at our conditions. So for our conditions, does the data come from a random sample? Data does not come from a random sample. And maybe I should say data does not come from random samples, because there's two samples. And if I was speaking is correct, I should say data do not come from random samples. Now I should type so you can read what I'm saying. Now these are a class of 21 and 23. So since those numbers are low, I'm going to have to graph those values. And when I graph them, I get one graph with a small standard deviation, and the graph below it has a little bit bigger standard deviation. And then I'd say something. Since there are no outliers in either distribution, we can assume sampling distributions are approximately normal. Now for independence, in this class, they did not randomly assign. So let's just say assume these students are all independent. All right, so we're assuming independence. We're talking about normality with the box plots, and they don't come from random samples. Wonderful. So now we can move on to calculations. So we won't need to find our values. Well, we have our X bar of our treatment to be 51.476, and our standard deviation of the treatment is 11.007, so let's just say 11. And if I did that for my second distribution, I have a mean of 41.5 and a standard deviation of 17.1. All right, now we have to say our test. We are using a two-sample t-test. And now let's look at our t-value. Our t-value, we take x1 minus x2 divided by square root of 11 squared, or s squared, over our n. I think the first one was 21. Go back and check. Yep, 21 and 23, plus 17.1 squared, all over 23. Now this is the opportunity that I would, you're more than welcome to do this, but I would go to your calculator and do a two-sample t-test and head on down and calculate it, and I get a t-value of 2.3, and that gives us a p-value of 0.013. Now that's all we have to do for our work. If we have this, our number set in the equation, we set it's a two-sample t-test, we have our t-value and our p-value, we're done. Now we just want to interpret. We reject the null hypothesis because our p-value of 0.013 is below an alpha value of 0.05. So we have evidence that the new techniques improved learning for the third graders. I think it's third graders. All right, that is a significance test.